Okay, so we're in 17.4. Still, we're talking about reaction rates. So we started in the first part of 17.4 talking about factors that affect reaction rates. And remember the things that we had. We said temperature can affect the reaction rate because it can speed up or increase the number of molecules that have enough energy to exceed the activation energy. Surface area could increase the reaction rate because there's more places to collide, and so we can have more successful collisions. Catalysts lower our activation energy, so that can increase our reaction rate. And concentration will have more stuff there available to react. Again, more collisions. It's always about having more successful collisions when we're talking about reaction rates. Well, now what we want to do is we want to write those reaction rates as equations, as terms for them. So here's how we're going to start. We're going to say the rate is proportional, or it could be proportional here, to a certain concentration, and typically it's going to be a reactant that's reacting. So the rate is proportional to a certain reactant. Notice they are going to be in brackets. They are going to be calculated in concentrations. So although we said we could measure reactions based on the changes in mass or the changes in volume, when we write reaction rates, they're always in reference to a concentration. Notice moles per cubic decimeter, or really molarity is how I'd like to think about them, or moles per liter, again, is our concentration that we'll be using. Well, if that concentration is influencing the rate, we're not going to write it as proportional. We're going to make a rate constant that we can throw in there so we can actually have an equation. Again, it's a rate constant. That rate constant might be rate constant, again, is going to be particular for the individual reaction we're looking at, but it does often vary on temperature. Regardless, let's look at what this means. So we have a rate that says it's equal to some rate constant. Again, we'll have that value from a table, that rate constant times the concentration of that one reactant. And again, in brackets, times that concentration. So what does this mean? And what this is telling us is if we take that concentration of A, and we double that concentration, so instead of having 0.1 molar, we put in 0.2 molar. Well, what that's going to tell us is that if we double that concentration, well, then the rate has to double. So instead of making, say, 2 grams of product per second, now we're going to make 4 grams of product per second. So if the concentration doubles, the rate doubles. That is what this equation is saying. This is what we would call a first order reaction. So it's first order. In a first order reaction, if we plotted the change in concentration, say, of A over time as it reacted, what we'd have is we'd have that similar graph that we saw in the other things, where the reaction is the quickest at the beginning, and then as we progress through it, it slowly tapers off until it plateaus at a certain level. Okay, we'd also have a second order reaction. So notice in this one it says the rate is proportional to the concentration squared. Now this is a little bit trickier if we have the concentration squared, so let's take a look at this. I'll move that to the side. Concentration squared, what is that going to mean? Again, we have the rate constant, and then we have this 2 here. Well, what that is telling us is this is a second order equation, or second order reaction. And what it means is that if we double the concentration of A, so I'll take the concentration of A and double it. So instead of having 0.01 molar, maybe again we have 0.02 molar, so we've doubled the concentration. Well, the rate in that case, if we've doubled the concentration, it is going to be doubled and then that squared. So it's going to increase by a power of 4 in this instance. So again, if we are measuring in this case maybe volume, maybe we're forming 2 cubic centimeters of gas per second. Well, instead of forming 2 cubic centimeters of gas per second in our first trial, we've doubled this. Now we're going to form 8 cubic centimeters per second. So notice it's a drastic increase in the effect on the rate if we have a second order reaction. So we don't just double it, we double it, or however much we increase this, that amount squared. So similarly, let's do this, let's change it. Maybe we triple it. Well, tripling it would mean, if we triple that, 3 squared means this is going to increase by a power of 9. So the rate's going to increase by a power of 9 because we've tripled the concentration, tripling it, and then we have to square that concentration. Is going to mean that rate's going to increase by a power of 9. Okay, a little confusing there. Let's go back a moment. Now we could also, just to define all the terms here, so we have a rate, and again, in most of these rates that we're looking at, it's going to be concentration per time. So the rate's going to be in units of concentration per time. Now, we're going to have rate constants. Those are things we can look up. Now, the rate itself could be with respect to A, or if there's another compound in it, it could be respect to B. Now, these are kind of generic. It's kind of hard to figure out what's going on when we're only dealing with A's and B's. But let's think of it like this. We could have A reacting with B to make compound AB. Now, one thing you might want to wonder is, say in our last scenario there, we had a second order reaction in respect to A. Now, why didn't influence B? Why wasn't B in there as well? Again, these are experimentally determined, so they have to do, back with a couple of podcasts ago, the reaction mechanism. So even though this might be our overall reaction, maybe, just maybe, A and A have to react to make A2, and then as A2, that reacts with B to make AB plus maybe more A. And so when we look at this series of reaction mechanisms, it could be this. That is our rate determining step. So our first step here might be rate determining, and that would be why our rate constant or our rate equation would only be written in terms of A and not in terms of the other compound that's there. A little bit confusing, but let's look at some real examples here. So here we have a reaction, and it says A and B react to form compounds R and S. Okay, so we have experiment number 1. We have initial concentrations and we have initial rate. Notice we don't even have units on that rate. It doesn't really matter right now. Now, what we're trying to do here is determine and write the reaction rate equation for this reaction. Now notice in the second experiment, they've kept the concentration of B constant, but we've doubled the concentration of A. So the concentration of A has doubled. Now let's look what happened to the rate. Notice the rate increased, but it increased dramatically. It didn't just double, okay? So it didn't just double. It's not a first order reaction. It increased by a power of 4. Well, if it increased by a power of 4, remember what we said, that means our rate equation has to be K times A squared. So it's second order with respect to A. But we can't stop there because we do have to look at B and see if B is affecting the rate. Now notice in the next set of experiments, they've kept A constant for the next series, but they have doubled the concentration of B. Notice doubling the concentration of B had no effect now on the rate of the equation at all. And so B does not affect the rate of the equation, only A affects the rate of the equation. So there must again be some reaction mechanism having to do with A that's influencing the rate of the reaction. Now let's look at the last step. Now they've increased A again. Notice we have an increase in rate, but here's what I want to see. I want to make sure that it is a second order reaction. So notice from 0.5 to 1.5 is increasing it by a power of 3. Now if it is, notice a second order reaction, this should increase by a power of 9, and notice it does. 0.002 to 0.018 is an increase of 9, so it is a second order reaction. 3 squared is our 9. So this is second order. All right, let's look at another example. Now this one kind of talks us through, but let's take a look at the numbers. Again, we have A and B, and all these examples are written in A and B. I apologize that they don't throw in some more real-world examples. I'll try to get some in here. So we start at 0.1 for each of these. We have our initial rate. It's in molarity per second. That's our initial rate. Notice in the first one, we've doubled the concentration of B. There's no effect on the rate. So the rate, we know right away, has no effect or increase in concentration of B has no effect on the rate. So notice, we would say that B is 0 order, or B to the 0 order, so it drops off. It's just 1. So if we want to include B in the reaction rate, we could, but we'd have to put it to the power of 0 because it really doesn't affect the rate. That's what we call 0 order. Okay, now let's look at A. If we look at the first example, now we've tripled A. And when we triple A, let's see what happens to the rate. Ooh, from 4.0 times 10 to the negative fifth to 3.6 times 10 to the negative fourth. So it has increased. Notice the exponent, negative fifth to negative fourth. There is an increase in the rate, but what is the increase? If we divide it out, we'll notice we can simply do this. 4 goes into 36. It's 9. So it increased by a power of 9 here. When we tripled this, that is second order. 3 squared is 9. So this is, again, second order with respect to A, which is what it tells us right here. Now notice our full rate equation would really have the constant times A to the second order, B to the 0 order. And again, a lot of times, if it's to the 0 order, they leave it off, and they just write that as second order with respect to A. Now notice what they do here is they actually plug in those values, and they calculate what that rate constant is. Because they have that rate, 4 times 10 to the negative fifth, they can throw that value in. They have that concentration, they can throw it in, square it. They can solve for the rate constant and carry that through to other reactions. Again, other reactions that are at the same temperature. That rate constant is temperature dependent. One more big example, let's see what we have. So in the first one, we have 0.001, 0.005, and 0.1 for C. So we have 3 reactants, which is kind of buggy, but that's okay. And we have an initial rate in reference to the concentration of A. Now notice we double A in the first one. We keep each of these constant, which we have to do. We can't change multiple concentrations at once. That'd get kind of confusing. Notice if we double A, notice what happened to the rate. The rate simply doubled. So this rate equation so far, in respect to A, is simply first order in respect to A. It does have an effect on the reaction rate, but there's not a huge increase in the rate. It's just a simple doubling, so it's first order. So far, that's my determination. Let's go on and see what else we can figure out. So now they put this back to 0.1, so those are constant. These are constant between the first and third trials. B, what have they done here? They've increased it by 0.5. Okay, so we can figure that out. They increase it by 0.5. What is the effect on the rate? Well, that again looks like a simple first order. So this is an increase of 1.5. 2.5 to 3.7 is an increase of 1.5. So 2.5 times 1.5, we would get 3.75. So it is first order with respect to B as well. Last one, we'll want to check. Now, why did they do this? This makes it more confusing when they don't run a good experiment. But they're just doing this to make it tricky for you. Okay, so notice, now we can compare these last two. Those haven't changed. They've done a doubling of C. Notice, and they've done a doubling of B. That makes it kind of tricky. It'd be nice if they held that constant, but they didn't. What do we know the doubling would do there? Well, we know this doubling of B, because we've already determined it first order, should simply double our reaction rate. So we would expect a doubling of our reaction rate from B. So let's see if it doubles. So 3.7, if we doubled the 3.7, we would have a reaction rate of 7.5 times 10 to the negative fourth. Notice our reaction rate is more than that. It is 3 times 10 to the negative, sorry, I wrote over it, third. So there's more than just a simple doubling of the reaction rate. So C does have an effect on the reaction rate, and now we have to figure out what it is. Well, it's more than just a doubling again. We'd have to ask ourselves, what is the increase from 7.5 times 10 to the negative fourth to 3 times 10 to the negative third? And if you divide those out, you'll see it's an increase by a power of 4. So ultimately, C had an increase of 4 times our reaction rate from what we predict based on just the doubling of B. So if it's 4 times, that means based on a doubling of this, that means it's second order with respect to C. So we wrote our reaction rate based on those. Kind of a crazy reaction. It'd say, what's the reaction order for each reactant? Well, again, it's first order. So A is first order with respect to A. First. First order with respect to B, and second order with respect to C. Now, one thing that we haven't talked about, what is the overall reaction order? Well, the overall reaction order would be to add these up. So the overall reaction order is to the fourth power, which is kind of odd, but it's fourth order. So we'd add up all the individual reaction orders, we get the overall order, and it says, what is K with the correct units? Well, we could do that. We'd plug in each of these concentrations, plug in a rate, and again, it doesn't matter which experiment we do, because we should get the same if we ran it at any of them.